The walking tour on Wednesday needs to be signed up by today, so if you can go to the front desk and you have to pay £5, but it's worth a trip around Cambridge, and they show you King's College and a few other things. So, but it has to be signed up by today if you want to do it.
Okay. Okay, so you can see our next speaker is George Carnevale from UCSD. So George, go ahead.
I've added equilibration to the talk, title of the talk, because that's mainly what I'll be speaking about. Not so much the instability, the centrifugal or inertial instability of a vortex, but how does the vortex re-equilibrate? What is the final product of a breakdown of a vortex through centrifugal or inertial instability? This work was motivated by rotating tank experiments in which we created a vortex in a rotating tank and watched how it evolved. And the process was fairly simple. We have a rotating tank with a fluid of a certain level, say 30 centimeters, and we insert a hollow cylinder into this tank and stir up the fluid within this hollow cylinder, let it settle down a bit until it becomes a cyclone or an anticyclone, more or less two-dimensional in structure with little vertical variation, and then we remove the cylinder. Oh, sorry, it's on. Yeah, this red light. It's okay? Nothing. I don't know. No? All right, I'll talk louder, I suppose. So you stir up the fluid in here, and then it settles down to a nice vortex, and you release the vortex to see what happens. And this is sort of typical of what happens when you have a strong anticyclone and you release it. And you see a phase right after the release. You're looking down here through the fluid from along the axis of rotation of the tank down through the fluid. And you see a phase of the motion right after release where it's very turbulent. It's very three-dimensional and vigorous motions. And then that slowly becomes more and more two-dimensional due to the effects of the background rotation. And eventually the vorticity gets sorted out, or even torn apart, you might say, separating positive and negative vorticity. And you see the formation here of two cyclones and an anticyclone forming a tripole, which is a fairly stable structure.
How do you know that it's three-dimensional? You look from above.
Oh, you see it from all angles in the laboratory. I'll show you some more of that. And then here again you see the turbulent phase right after release, another anticyclone. Again, it goes into a stage where it's more or less two-dimensional. It's two-dimensional more and more as the time goes on. And you can see these things like Taylor columns that are very straight up and down. I mean, geometrical structures. They're very nice to see in the laboratory. And eventually, again, you're pulling apart positive and negative vorticity. And here you formed a double dipole structure with a cyclone, anticyclone, and a cyclone and anticyclone here. Two dipoles that move apart from each other. And then typically what you see is the formation of dipoles or double dipoles or tripoles or monopoles as the end products of this kind of an instability. We've been able to more or less reproduce this in three-dimensional numerical simulations. So here we're looking at a three-dimensional numerical simulation where I'm plotting omega z, and I'm looking at one level of a three-dimensional simulation and just following the evolution of omega z. And you see something like what we were seeing in the laboratory. This is for an anticyclone. And here we have a cross-section through the vortex. Now this is a vertical cross-section. And here we see an instability beginning. I start with a two-dimensional vorticity profile. In other words, there's no variation in z. And you see this variation start because we've added a little noise, and that starts up an instability. And then you see it become very three-dimensional very rapidly. And then things begin to sort out and become more and more two-dimensional as time goes on, and you wind up here with three vortices, the two cyclones and the anticyclone in the center. Now, it's nice to go back to the very early phase of this and look at the instability that's starting this whole process off. And here I'm plotting omega theta, which is the perturbation vorticity. That's the azimuthal vorticity, and there's zero azimuthal vorticity in the initial condition. So this starts up as the instability grows and it becomes stronger and stronger. And you see that the form it takes here, these are positive and negative vortices, but what they really are is rib vortices. They go around the entire vortex. And this is typical for an inertial or centrifugal instability. And we usually think of this in its pure form as an axially symmetric instability. So if you have a vortex here, and the velocity field, the azimuthal velocity field of the main vortex is like this, the instability takes its form as a series of toroidal vortices encircling the main vortex. And this is the signature of centrifugal instability. The other part of the process is the separation of positive and negative vorticity near the end, which is a barotropic instability. And the barotropic instability is very well studied. There have been many papers on that, and we have a very good handle, a very good understanding of what barotropic instability does. For certain simple profiles of velocity, you can predict analytically what it will do. But you know, in the worst case scenario, if you give me a complicated velocity profile to start with, it's just a two-dimensional problem, and you can just solve it two-dimensionally very quickly numerically. So we can predict what the outcome of barotropic instability will be very easily. But what we did here was we studied centrifugal instability to see what centrifugal instability alone would do, and what we're going to try to do in the end is put the both of them together and see what we can predict. So centrifugal instability, the criterion for centrifugal instability goes way back to Rayleigh, where he argued from simply looking at an axisymmetric flow, axisymmetric dynamics, and interchanging two rings of fluid, and looking at whether or not you release energy or not by interchanging rings of fluid. And under the constraint of angular momentum, he found that the only way you could get energy out of such a process would be if the angular momentum decreased in magnitude with distance from the center of the vortex. So the criterion becomes that the gradient of L squared has to be less than 0, or L times LR has to be less than 0, LR being the derivative in the radial direction. L is just the absolute angular momentum of the problem in our system. Rayleigh wasn't dealing with a flow in an ambient rotation, but if you add the ambient rotation, since he was in an inertial reference frame, the appropriate thing to do here is L becomes the absolute angular momentum, where we include the background rotation now. And its derivative is just R times omega plus F, the Coriolis parameter. So this is essentially the potential vorticity here of the fluid. So the absolute angular momentum times the potential vorticity essentially has to be less than 0 to get instability. And you will have instability under that condition. Now, another thing we've added to this, we were interested in what role stratification might have. What if you did these experiments stratified? What would we expect? So we've done a lot of simulations with stratification as well as the background rotation. But for simplicity, I'm only going to talk about the barotropic case. So we always start with a main vortex that has no vertical variation to begin with. And under those conditions, the theory is the same. The prediction is always that you need this product to be negative to get instability. It's the same criterion again, even with the stratification. Okay, well, we've done many numerical simulations with many different families of initial conditions, and this is one of them that I've done most of the experiments with for various reasons. And it's, you know, just a parameterized family of velocity profiles, and we have this parameter alpha, which turns out to be very important. It's we call it a steepness parameter. So the larger alpha is, the steeper the fall off of the velocity in the velocity profile. Again, this is azimuthal velocity. This is non-dimensional form. In dimensional form, there'd be some characteristic velocity scale and a characteristic horizontal length scale. And from that, you can form a Rossby number, which is also very important in determining whether your vortex is centrifugally stable or not. And then, of course, a Reynolds number. And most of what I'll show you is with alpha equals 3, but we've looked at a wide range of alpha values. Just to show you what typically happens, you've got some stratification here. N squared is 2. I'm non-dimensionalizing with F, the Coriolis parameter. This is a Rossby number -1. That means an anticyclone with Rossby number 1. And this is early times. And what I'm plotting here is just the radius from 0.6 to 1.6, where most of the action will occur in this experiment. And the vertical lines here show you where Rayleigh's criterion says it's linearly unstable. So we expect the instability to grow in here. And in fact, in the early evolution, that's what you see. You see the formation of these, again, these rib vortices. Now they're a lot flatter than the original picture I showed you in the three-dimensional simulation. This is an axisymmetric simulation but they're flatter because you've got stratification now, and the higher the stratification, the flatter these things become. But what you typically see is as these things grow, they begin to move out of the region of instability. They form more or less dipolar heads here and here, and move inward and also outward from the instability region. So you see them beginning to move in and out, becoming rather vigorous, and then eventually engulfing much of the vortex. It's interesting to look at what happens to the profiles. If velocity, I can make an average profile velocity by averaging through the vortex vertically. And so what we've got here is velocity versus r, the radius. And here's the initial profile at t equals 0. And then it quickly collapses as time advances up to about t equal 80, which is about 7 rotations of the background of the tank. It collapses to this profile, which more or less remains for a long period of time as viscous decay takes over. So through this point, through this period here, the centrifugal instability is rather vigorous, and it's doing what it's doing. And then you wind up with a more or less a linear profile at the end of the centrifugal instability. At this point, there's very little evidence of the centrifugal instability. It's very weak. And after this, we just have more or less viscous decay. It's nice to look at what happens to the absolute angular momentum now. You see that the angular momentum originally is like this. This is the instability region, because here we have L is negative and LR is positive. And so that gives you the instability criterion being satisfied in this range. During the centrifugal instability, this collapse is becoming flatter and flatter and flatter. Now, if you look at it, it's not quite stabilized, because here you still have LR as positive and L is negative, but we also have finite viscosity now. So it seems that the viscosity, the presence of viscosity, could stabilize this or quench or stop this instability from proceeding, even though the inviscid stability criteria is still satisfied. Now, what happens to the velocity profile if I fix, as a function of the stratification, is also interesting. If I fix the Reynolds number, this is a fairly high Reynolds number now, and then I look at what happens at high n squared, it still collapses to a linear profile, but as I make n squared smaller and smaller and smaller, I'm getting closer and closer to solid body rotation, which is the straight line here. And it goes out well beyond the instability region, well into the core in this direction, and then well beyond the instability region, and then drops off rather rapidly back to the original profile for high R. It's also interesting to look at what happens with a fixed n squared. This is a very high n squared now. It's very stratified. But what happens as the Reynolds number becomes higher and higher and higher? As the Reynolds number gets higher, you go closer and closer, perhaps, to the solid body rotation case.
The whole time is in flux here.
Yes, I'm sorry. This is after the centrifugal instability is finished. So this is the final state.
Nothing happens
Slow viscous decay. And if you look at lower n squared values, you see you get even closer and closer to solid body rotation for any n squared as the Reynolds number increases. If you look at what's happening to the angular momentum, again, this is a high n squared, but still what we see is a collapse of the angular momentum to a flatter and flatter regime here, and again, a return to the initial unperturbed state over here. This is going through Reynolds number 10, 20, and 100. So the higher the Reynolds number, the flatter the angular momentum becomes.
I'm really confused.
Yeah.
You have flat angular momentum yet rigid rotation. How can that be? You say you had solid body rotation and yet you had flat angular, uniform angular momentum.
Well, here, for example, this is the final upshot of the thing. What I'm suggesting is that the flow, as you take the limit of going to infinite Reynolds number, you wind up with zero absolute angular momentum.
With zero.
Yeah, zero absolute angular momentum here. And yeah, and this seems to be the result of many experiments where we just take the limit of the Reynolds number getting higher and higher. It looks like for any n squared, we're going to this final result. Zero absolute angular momentum out to a certain radius, RC, and then it jumps back to the initial profile, the unperturbed profile. So what we're getting out of this is an idea that we can predict how far out the instability will go. And so what we've got here is a little prescription. So what we're saying is that we've got a deficit of angular momentum here, negative angular momentum here. We're going to balance it with the positive angular momentum there, mix them together, conserving angular momentum. We've got a formula to calculate RC. So we can easily calculate how far out we can expect the centrifugal instability to go and the final profile. It didn't have to do that. There's an infinite source of positive absolute angular momentum out here that it could have mixed in, but it doesn't. It seems to stop right there, right at RC, and it seems to be a fairly good prediction. This is the velocity field that we're predicting. And again, many of the simulations seemed, as we were increasing the Reynolds number as far as we could, seem to be going to something like this. So that's why we're suggesting that this is a reasonable result. So again, you've got solid body rotation here. Absolute angular momentum is 0, so the velocity is minus omega r. It's just matching the rotation of the tank, but in the opposite direction, in the core of the vortex. And then it drops rapidly back to the unperturbed state outside of it, outside that core. And the limit is, again, given by our formula, which is just angular momentum conservation during the mixing. Cyclone is interesting because the profile is rather different, but a similar principle will apply. So you take, this is a typical cyclone for this family of vortices, a typical graph of angular momentum. And you see you're going to have instability in here because L is positive, but LR is negative. And so now we have, here's two experiments where I'm just showing you the last phase where the centrifugal instability is finished. And this is for Reynolds number 10,000. And you see it curve moves like this, fairly smoothed out. But as the Reynolds number gets higher and higher and higher, it does appear to be flattening out in this region here. The instability region goes from here to here, but we're flattening this out between here and here, much further than the instability region alone. All that does to the velocity profile is not much. The thin line is the initial velocity profile. The thick line is the final velocity profile. So in this case, we're just changing the steepness of the velocity profile a bit. What's remarkable about this diagram is there are actually two thick lines here, and they're lying right on top of each other. One is for n squared equals 0, one is for n squared equals 50. So the stratification, although it changes the dynamics tremendously, the pictures are very different, looking at the dynamics and the evolution of the 0 stratification case and the high stratification case. Yet in terms of the final mixing of angular momentum, it doesn't make any difference. You wind up with the same profiles. And so now what we're suggesting for this case is that equilibration, independent of n squared, will always take this form. You'll mix angular momentum, and you can calculate how much just by considering a constant level of angular momentum going through this region and asking, can I balance this excess of angular momentum here with this deficit here? And just by drawing the straight line across here, then I can calculate this integral for any LC that I assign and therefore calculate which LC is the correct one. And that way we can have a prediction of the minimum radius and the maximum radius over which the angular momentum will be mixed. And outside that, we just return to the original profile. And this also seems to work very well. Here we've tested it. Well, here's what it does in the case that we've been talking about with alpha equals 3 and Rossby number 1.4. You see that again, it just changes the slope a bit of the velocity field, so just like in the experiment. But here's a more extreme case. Here's a Rossby number 4 cyclone. And in this case, the initial profile and the final profiles are rather different. The solid line is the prediction from the simple prescription, the simple construction, and the circles come from an axisymmetric numerical simulation. Now, just to emphasize, we were thinking we would expect to see mixing or homogenization of potential vorticity, and that's what you do see in the region where instability is predicted. Our question was, how far out does it go on the sides? And you know, you could have mixed in a lot from out here or mixed in a lot from there. It wasn't clear at first how much you would be mixing in. And it was just surprising over and over again as we took the limit to high Reynolds number, it just really seemed to be cutting off at these 2 points, which were rather simply predicted from those constructions. So now we're at the stage where we've got 2 theories. We've got barotropic instability, we know a lot about that, and now we know something about the centrifugal instability, that's tendency, long time tendency. Can we put them together somehow to make some predictions? And so what we're doing here is taking a fully 3-dimensional simulation at some Rossby number and some alpha, and watching what happens to it and the final products. And now we're going to compare it with taking the initial profile, assuming that centrifugal instability works to completion, and that gives us a new profile. So just the prescription alone gives us the new profile. And then we take the new profile and use either barotropic theory or, in other words, take a 2-dimensional simulation and run that profile out to its final products and see how close we can get. And I do this first with alpha equals 1.8. 1.8 is special because it's on the borderline. There's no barotropic instability when I start in the 3D case. Centrifugal instability does start first, and then you're followed by barotropic instability. And it works fairly well. Here's the prediction based on that simple scheme. And then here's the result of an actual 3D, fully 3D simulation. Now, the timescales aren't going to match up because in one case I'm just jumping over the centrifugal instability, I'm not simulating. And this is the time after I've started the barotropic simulation. But you find the end products look very similar. Here's another case where I've gone up to Rossby number -3, so this is a much more vigorous anticyclone. Here's the 3-dimensional, fully 3-dimensional simulation, and then the prediction. Again, they look very similar. Now, the real test, I think, it will be whether the regime boundaries match up, and it seems to do fairly well there. So I've simulated from Rossby number -1 up to Rossby number -3.5 to look at where the products are different, the end products are different. In this regime, you get monopoles, so the centrifugal instability isn't strong enough to actually push you into a barotropic instability. And here we get tripoles, and here we get double dipoles. But the regime boundaries match up fairly well. Here we've got -2.2, here we've got -2.1, -2.3 here, -2.4 here. But what I notice is when I do this at lower Reynolds number, I get worse results. And the nice thing is as I increase the Reynolds number, it gets closer and closer. The two compare very well. Again, this is perhaps the best case to test this in terms of best for the predictions, because we do know that we have to start out with centrifugal instability in this case. We've pushed this up to about -3 now, where both are competing, and it still seems to do fairly well. So the question is, how far up in alpha can I go? How far up in Rossby number and alpha can I go, where both instabilities are really very active initially, and can I still make predictions like this? And maybe another question is, will there be a crossover in which the barotropic instability occurs first and then centrifugal instability follows after? Can we still use these things in some combination to get reasonable predictions of what the final state of these vortices will be? And this may be useful if if you see a vortex and you don't want to have to do the whole 3D simulation to figure out what's going to happen to it. Maybe you can use simple ideas like this to predict what the final vortices will look like. Thank you.
Just check. Supposing you had 0 background rotations at Rossby number going to infinity, does everything collapse completely, or can you still have something stable?
Well, 0 background rotation, you wind up with turbulence.
So essentially nothing can be stable.
Yeah, I mean, you don't
can't have a
stable.
stable axis.
There's nothing that's stable. Yeah.
Question in the back.
Yes, your vortices are tall vortices, so they are
Yes.
longer than they are large.
They're about 1 to 1.
1 to
They're
1.
not that different. Yeah.
Well, in the ocean it's like 1 to 10, so it's
Oh, yeah,
10
sure. Yeah.
or so. So
It's harder to simulate though if you want to put the resolution in both directions.
yes.
Yeah.
So the instability in my simulations, what I see, appears at where it's the most unstable area, and then the size of the instability corresponds to the depths of the ocean at that point. So you wouldn't have these.
Right. I mean, if you make it
Dynamics,
so,
I guess.
yeah. I mean, what's picking out the size of the eddies or the size of the vortices, the rib vortices, is a combination of the viscosity, the Reynolds number. The higher the Reynolds number, the smaller structures you get. So yeah, if you do the simulation in a very narrow flat box, you won't see the centrifugal instability at all because the cell size isn't there.
It actually creates filaments more
Yeah.
than other structures.
But I don't know, if you go to higher and higher Reynolds number, the centrifugal instability goes to smaller and smaller scale. So I'm not quite sure what you will see then. But of course, also when you're using very thin fluids, the thickness alone can make the flow two-dimensional and prevent the thing from going three-dimensional. So you wouldn't see the centrifugal instability if it was very thin.
You always see it, but it's three-dimensional, so the horizontal size is governed by the depths of the ocean.
Yes. Okay.
You mentioned that the centrifugal instability criterion is not affected by the stratification.
It isn't when you have barotropic initial conditions.
Because I remember there were experiments with the Taylor vortex
Yeah.
case. They can see that the stratification is actually destabilizing the occurrence of Taylor vortex.
Yeah, interesting. I'm not sure.
That's experiments by Lebar and the guy.
Yeah, I think, in terms of the theory that the stratification wouldn't make any effect. For the barotropic case, now, I don't know, the baroclinic case is rather different because then, once you go baroclinic, the isopycnals are sloping. In the cases I was talking about, the isopycnals are flat. But once the isopycnals begin to slope, then the instability occurs curved along the isopycnals. And all the mixing is going on along the isopycnals. But as you mix along the isopycnals change their shape. And the problem becomes much more complicated. So,
Michael?
This phenomenon of three-dimensional motion
yeah.
bringing not just PV homogenization, but actually zero PV in
Yeah.
certain regions. It reminds me of some interesting work I heard about by a young man who used to be at Woods Hole, I believe now at Stanford, Leif Thomas, who was considering a wind-driven ocean jet. And on the anticyclonic side of that, he seemed to be getting that kind of thing with zero
Oh,
PV
nice.
from three-dimensional motion.
Nice, okay. And that name was?
Well, I mean, zero PV is a transition to symmetric instability, right?
Of course.
Yeah.
Which is why, this is bringing out
Which
nicely.
is very
how-
I mean, alignment of density surfaces and absolute momentum surfaces.
Mm-hmm.
Yeah,
Yeah.
Leif Thomas's work.
Leif Thomas. Yeah, good, thank
So
you.
it's the zeroness as well as the homogenization that's
Right.
key
Yeah.
here.
Yes.